In this lesson, we'll review the definition of a random variable and probability distributions. We'll discuss several examples of special types of distributions and consider various applications. If we roll a fair die, the possible outcomes are the numbers 1, 2, 3, 4, 5, and 6. Now each of these numbers has probability 1/6 of appearing. Rolling a die is a probability experiment whose outcomes are numbers. The outcome of such an experiment is called a random variable. Now rolling a die is a simple example. However, random variables are all over the place. Examples include the number of visits to a certain flower by different pollinators, the proportion of a certain genetic trait in a population, the number of offspring produced by a particular type of insect, the success rate of a medical experiment, the survival rate of a species within a given environment, the number of mutations in a genetic sequence over time. Some random variables are discrete, that is, the outcomes can be listed or counted. Other random variables are continuous, where the outcomes can be any value within an interval, meaning that the outcomes must be measured as opposed to counted. For now, we will concentrate on discrete random variables. A probability distribution for a discrete random variable specifies the probability for each possible value of the variable. Let's look at an example. Let y be the number of female offspring in a litter of 3 produced by a coyote. Suppose that the probability of an offspring being female is 0.5. We want to find the probability distribution of y. So here there are 8 equally likely outcomes. Let's list these possibilities out. Now we count up the number of female offspring for each outcome. We see that there are 4 possible values of the number of female offspring: 0, 1, 2, and 3. If we divide the frequency of each outcome by the total number of possibilities, which is 8, then we find the probability of each outcome of y. This gives us the probability distribution of y. It will sometimes be useful to look at the probability histogram to get a graphical depiction of the distribution. Now let's take a moment to discuss the difference between a distribution of data and a probability distribution. A distribution of data shows actual values that we have and how frequently they occur. We can discuss the shape of these data and how they are centered and spread out using measures such as the mean and the standard deviation. In contrast, a probability distribution is a theoretical construct. It's a model used to explain the data and a best guess as to what can be expected. In practice, we often use a given data set to estimate the parameters of a probability distribution, with the goal of finding a model that fits the data well so that it can be used to make predictions about future data. Think of a data set as a dish. You can determine how it looks and tastes and describe its various features. A probability distribution, on the other hand, is kind of like a recipe. It tells us the ingredients and the steps necessary to create future dishes. Now, given a discrete random variable y, we can find the mean of y denoted by mu sub y. The mean of a random variable is a measure of center. It's also referred to as the expected value because it provides the value that we expect to get on average if the probability experiment is repeated over and over. The standard deviation of y, denoted by sigma sub y, is a measure of how spread out the probabilities are. Consider again the probability distribution of y, the number of coyote female offspring out of 3. We will find the mean and standard deviation. We're going to use R. Let's first define a data array for the random variable outcomes. We'll call it y. Now, define a data array for the associated probabilities. Let's call this prob.y. To find the mean, we need the products of y and prob.y. Then we take the sum of the results. I'll call the mean mu.y. We find the mean to be 1.5. Remember, the way to interpret this is that in a litter of 3 coyote pups, on average, the number of female offspring is 1.5. The standard deviation is a little more complicated. Let's start by finding y squared times prob.y. Next, we need to sum these results. We will need to subtract the square of the mean. And lastly, we will take the square root. We find the standard deviation sigma.y to be approximately 0.866. We now consider binomial distributions. In 1963, psychologist Stanley Milgram conducted experiments to investigate how authority influences obedience. A typical experiment involved a participant receiving instructions from an authority figure to administer increasingly intense electric shocks to a stranger. Milgram discovered that only 35% of participants disobeyed the authority and halted the shocks before reaching the maximum level. Subsequent studies have revealed that this percentage of disobedience is relatively consistent across different cultures and eras. Each person in Milgram's experiment can be thought of as a trial. If we suppose that a trial is labeled as a success if the person refuses to administer the maximum shock, then the probability of a success is p equals 0.35. The probability of a failure, administering the maximum shock, is then q equals 1 minus p, which is 0.65. The quantities n and p are called the parameters of the binomial distribution. We must know these to find various binomial probabilities. Probabilities of a binomial random variable can be found using the probability density function. However, we'll find these probabilities in R. The domain is the set of all possible values of the random variable. For a binomial random variable, the domain is y equals 0, 1, 2, 3, all the way up to n. It can be shown that the mean is mu sub y equals n times p, and the standard deviation can be shown to be sigma sub y equals the square root of n times p times 1 minus p. Often, we express a binomial random variable y using the following notation. Let's take a moment and look at the binomial distribution in the online graphing calculator Desmos. Note how the shape of the distribution changes for different values of p. In R, there are several commands associated with the binomial distribution. The dbinom x, n, p command finds the probability of exactly x successes. The pbinom command finds the probability of x or fewer successes. The qbinom command with parameters percentile, n, p finds the trial number corresponding to the given percentile. Let's look at an example. Suppose that in one run of the Milgram experiment there were 20 participants. Here, the number of successes, that is, the number of participants who did not administer the maximum shock, has a binomial distribution with n equals 20 and p equals 0.35. Let's go ahead and define n to be 20 and p to be 0.35 in R. Now, what is the probability that 7 participants did not administer the maximum shock, that is, 7 successes? We find this probability with the dbinom command, where x equals 7 and the given values of n and p. We find the probability that 7 participants did not administer the maximum shock to be 0.1844. What is the probability that 7 or fewer participants did not administer the maximum shock? Here we can use the pbinom command, where x equals 7. The probability of 7 or fewer is 0.6010. Now we could also find this probability by computing dbinom using the data array from 0 to 7, and then summing the results. Here we are finding the probability of each value of x from 0 to 7, and then just adding those values together. What is the cutoff of the top 20% of successes? That is, the number of participants that is the 80th percentile. We are looking for the 80th percentile. We use the command qbinom 0.80, n, p. The 80th percentile is 9. Let's consider another example. It might be useful for you to try this one on your own in R. Then continue the video when you're done to see if you got it correct. In a random sample of 260 stocks of Drosophila melanogaster flies, approximately 30% are infected with Wolbachia, an intercellular microbe that can manipulate host reproduction for its own benefit. What is the mean number of stocks that are infected? What is the probability that at least 65 stocks are infected? Okay, here we call a trial a success if it is infected with Wolbachia. The number of trials is 260 and the probability of a success is 0.30. The mean number of stocks is given by n times p, which is 78. The probability that at least 65 stocks are infected can be found by computing the exact probability for each value of x from 65 to 260, and then summing the results. We find the probability to be 0.9679. Let's move on to the geometric distribution. Consider again the Milgram experiment. Recall that approximately 35% of the participants halted the shocks before the maximum level. We have already seen that the random variable y that counts the number of successes follows a binomial distribution. Suppose now that instead of counting the number of successes, we are interested in the number of trials it takes before the first success. Another way of thinking of this is the number of failures that must happen before the first success occurs. The distribution of the random variable that counts the number of trials it takes before the first success is called a geometric distribution. The domain of a geometric distribution is y equals 0, 1, 2, 3, and so on. Note here that y can be infinite because theoretically we could have trial after trial and never get to a success. Now let's take a quick look at the general shape of a geometric distribution for various values of p. The mean of a geometric random variable is mu sub y equals 1 minus p over p, and the standard deviation is sigma sub y equals the square root of 1 minus p divided by p squared. In R, we can use the d geom x comma p, or p geom x comma p, or the q geom percentile comma p commands in much the same way as we did for the binomial distribution. Let's look again at the Milgram experiment where p equals 0.35, the probability of not administering the maximum shock. Let y be the number of participants who administer the maximum shock before we observe one who does not. Then y follows a geometric distribution with p equals 0.35. What is the probability that the first participant that doesn't administer the maximum shock is the third one? Remember, the geometric random variable counts the number of failures before a success occurs, so we are looking for the probability that there are 2 failures before a success on the third trial. We use the command dgeom 2, 0.35. We find the probability to be 0.1479. What is the expected number of participants who administer the maximum shock before coming across one that doesn't? The expected number of participants who administer the maximum shock before coming across one that doesn't is the mean of y. We find the mean to be the quantity 1 minus p divided by p, which is 1.86. If we wanted to be 90% sure that we observe a participant who did not administer the maximum shock, how many participants should we watch? We want the 90th percentile. Using the qgeom command with 0.90 as the percentile and 0.35 as p, we find that we should watch at least 5 participants. Consider another example. Again, it might be useful for you to try this on your own before coming back to the video. In a population of cattle, approximately 48% are infected with leptospira, a bacterial disease. Suppose that individuals from this population are randomly selected and tested for leptospira. What is the probability that the first to be tested is positive? What is the probability that the first to test positive is one of the first 5? Let's define p to be 0.48. To find the probability that the first to be tested is positive, that means we want to find the probability that y equals 0. The dgeom 0, p command gives us 0.48. Note that this shouldn't be a surprise. If the probability of a success is 0.48 on any given trial, then the probability of a success on the first trial is 0.48. Now, the probability that the first to test positive is one of the first 5 is found by computing p of 0 or 1 or 2 or 3 or 4. Remember here, y is counting up the number of failures before the first success. We can either find this probability with the pgeom 4p command, or by summing up these probabilities with a dgeom command. Let's consider another type of random variable. We begin with an example. The average density of penguins in a particular region is known to be 49. Suppose an ecological study will be done in the region. We want to know the probability of observing at least 60 penguins. A Poisson random variable often provides a good model for the number y of rare events that occur in time, space, or volume when we know the expected mean lambda. Probabilities of a Poisson random variable with mean lambda can be found using the probability density function, or with similar R commands that we've seen before. The domain of a Poisson random variable is y equals 0, 1, 2, 3, and so on. The mean is a parameter of the distribution and equals mu sub y equals lambda. The standard deviation can be shown to be sigma sub y equals the square root of lambda. We use the following notation to denote a Poisson random variable. So let's go back to the example. The average density of penguins in a particular area is 49. We want to find the probability of observing at least 60 penguins in an ecological study of the region. The dpois x, lambda command will find the probability of exactly x events. As in previous examples though, x can be a data array, so we could use something like sum dpois, where x goes from 60 to some really large number, like maybe 10,000, and the mean is 49. Although the domain of a Poisson random variable is infinite, in reality we can be sure that there will not be more than 10,000 events when the average number is only 49. We find the probability of observing at least 60 penguins is 0.0703. Would it be unusual to find no more than 40 penguins? We can either use the ppois 40, 49 command, or sum the probabilities associated with the values 0 to 40. We find this probability to be 0.1098, which is not particularly an unusually small value. It means that we would expect to find no more than 40 penguins about 11% of the time. Generally, we will use a cutoff of 0.05, which corresponds to 5%, to categorize something as an unusual event. Would it be unusual to find no more than 35 penguins? Rerunning the command with an upper limit of 35 yields a probability of 0.0225. It would be unusual to find no more than 35 penguins. Let's look at one last example. In an experiment with an enclosed space, a little brown bat, Myotis lucificus, was found to consume 890 fruit flies per hour. Suppose that a random bat was studied under similar circumstances. An often mentioned statement claims that bats can eat 1,000 insects per hour. Find the probability that the studied bat consumed at least 1,000 fruit flies per hour. What's the probability that the studied bat consumed less than or equal to 450 fruit flies in half of an hour? Would it be unusual for the studied bat to consume at least 1,400 fruit flies in 1.5 hours? What is the third quartile of the number of fruit flies consumed in a 2-hour period? Okay, we're going to model this experiment with a Poisson random variable, with mean lambda equals 890. The probability that the bat consumed at least 1,000 fruit flies per hour is 0.00016. It sounds like the claim that a bat eats 1,000 insects per hour is probably an over-exaggeration. What's the probability that the studied bat consumed less than or equal to 450 fruit flies in half of an hour? Now we have to be careful here. This question asks about a probability in a half-hour period. We know that a bat eats an average of 890 fruit flies per hour, which means that it eats 890 divided by 2, which is 445 per half hour. We find the probability that the bat consumed less than or equal to 450 fruit flies in half of an hour to be 0.6057. Would it be unusual for the studied bat to consume at least 1,400 fruit flies in 1.5 hours? Again, we need to adjust the mean. 890 fruit flies per hour equates to 1.5 times 890, which is 1,335 fruit flies in an hour and a half. The probability that the bat consumes at least 1,400 fruit flies is 0.0396, which is fairly unusual. What is the third quartile of the number of fruit flies consumed in a 2-hour period? We will use the qPois command. Be sure to adjust the mean to a 2-hour period, and recall that the third quartile is the same as the 75th percentile. We find the third quartile to be 1,808. Okay, so that wraps up this lesson. Best of luck as you move forward with the quiz.